Well, hey everyone, and welcome back. The purpose of this video is to kind of tie in a concept that I covered in a much earlier video, strike and dip, and apply it to what I've been talking about recently, which is folding. Now, as you know, folds are a type of deformational structure within geology. And so when we think about them, there's always going to be a strike and a dip associated with them, right? They're going to be strata that's dipping in a certain direction, and though sometimes we don't picture them at the surface, the structure that we see popping through at the surface is going to be striking in a certain direction. So previously, when I've done problems involving strike and dip, I've kind of just given values and made it look very sort of textbook problem style-esque. But I figured with this video we try to make it seem more like an actual geological experience, right? So let's say we've got a map here. Doesn't have to be super detailed, but it's a top-down view of just an area, right? That's just an area. It doesn't really matter how large it is yet. In the real world, we'd have exact specifics, but for this example, we don't necessarily need them. So let's say we've got a compass that goes along with that map, and it's one of our traditional north is upwards, south is downwards, east, west compasses, right? Now let's say that we've got a line that goes through like this. Just a line right in there. And someone tells you that at that line there is a syncline, okay? Right here, there is a syncline. So you go and check out that line. Maybe there's a piece of it that sticks through so you can actually observe it. And you create a cross-sectional profile of this region that looks something like this. You just draw out the syncline that you were informed of. Just looks something like that. Our traditional, nice-looking syncline shape. Just like that. Okay, so you've found what this region looks like two-dimensionally. You found what's going on with the strata there. But if we actually want to get some data on this region, such as the strike and dip, then what we're going to have to do is first consider, we have to find the compass directions from this map that would be applied to this piece right here. So what we can do is just kind of imagine this line as a compass bearing, right? Or maybe not a compass bearing, but going through a sort of coordinate plane where that's north, right? And then the rest just sort of fills itself in. So if I just try to replicate this here, it's not going to be perfect, I know. But it will look something like that. So we'll say that this right here, we'll say that that's, I don't know, maybe about 30 degrees east of north. Or 30 degrees, just flat out 30 on the compass. Because you remember, north is 0 or 360 degrees, and then that's 90, 180, 270, and so on. So actually we can just call that 30 degrees. And then if we carry this downwards, then the other angle that is made appears to be, you can think of it in two ways. One, we know that this must be 30 degrees as well, because of that one, I don't know, thinking back to geometry, that one theorem that states if you've got two angles formed by two lines, then they are going to be congruent. So you can say that's 30 degrees west of south, or you can simply say, well, this is just a 180 degree, it's just 180 degrees more than this angle, so therefore it must be 30 plus 180 is 210 degrees. So we can write that as 210 degrees or 30 degrees west of south. So these two pieces are important because, as you recall, dip has two pieces. It has both an angle and a direction. So if we were to look at the dip of, say, this limb right here, remember the dip angle is always going to be the acute angle, right? So that's going to be right here, the angle it makes with the surface that is acute. This one right here on the other side, that's obtuse, so we wouldn't use it. But the acute angle that is within here, that's going to be our angle of dip, and the reason we need these is because dip also has a direction. So when we look at this, we say, okay, 30 degrees east of north, and 30 degrees west of south. Which way is it dipping? Well, it's going in this direction, which means it is dipping towards 30 degrees east of north. So just kind of take away the vertical component of this line, and you'll be left with a horizontal component that is going in this direction. Therefore, we say that the direction of dip is towards 30 degrees. So, I don't have a protractor here, that's why I kind of estimated that angle. But this angle looks to be about, I don't know, looks like it's almost 45 degrees maybe. We'll call it 45 degrees. That is a 45-degree angle, and that is our angle of dip. So now, with this information, we can say that the dip is 30 degrees east of north. That is the direction at 45 degrees. That's the actual angle. Now don't let this confuse you. This is still the direction. Just because we can represent the direction sort of on this coordinate plane bearing style, that doesn't, don't get confused by multiple angles being in here. This is still the direction and this is still the angle. That's why usually I separate the two by saying at with this little at direction at angle. Yeah, I think that's a pretty good formula to go by. And then if we want to talk about the strike, well, how do we do that? Because as you'll recall, strike usually deals with the surface, and from these two pieces of information we have, well, we don't have any image of what the surface could possibly be. However, also recall that the strike is much simpler than the dip in that it's simply a cardinal direction. We have no angle to take into account, and strike's just, you know, your cardinal direction. So from these two pieces we can't determine it, but a very useful piece of information that can save you a lot of time, say in this case it would save you a trip going back to this actual region in the middle of nowhere and looking at the strata and actually determining a strike based on a compass reading. What you can actually do is just know that strike is always perpendicular to the dip, right? It's always 90 degrees to the dip. And not only that, because you'll notice that if we look at the dip direction, well, this is on a coordinate plane, or actually it's this line. The dip is on a coordinate plane, so what do we consider to be 90 degrees to the dip? You know, you can form a 90-degree angle like this, or like this. So what do? Well, the way I think of it is strike is always 90 degrees less than the dip. That's determined using the right-hand rule usually. But strike, the direction of strike is always the 90 degrees less than the dip. Dip is always 90 degrees greater than the strike. That's the relationship they have. So in this case, strike, we would look at that. Okay, 30 degrees here minus 90. This is going to be 60 degrees west of north. And that's your strike. So now we have both the strike and the dip. So if, say, we had a piece of strata labeled here, or maybe we don't even need it, we can just write on this top-down map a nice little strike and dip symbol, which you'll recall looks something like this, just an example, and then you write your angle right there. So if we wanted to write that in on the map, then we have to draw our strike going at 60 degrees west of north. Strike is always the bigger line, so we'll try to draw this. Strike's going to be like that. That is the direction at which our strata strikes. And then if we want to write the dip, then we just draw this bad boy in. We make that perpendicular, that's always the shorter line. And then we just write in our dip angle somewhere close to it, 45 degrees. And that's our strike and dip symbol. So through this process we've taken a top-down view of what we know is a syncline, assumingly by some sort of process of going to the actual, going to the region itself and looking at a cross-section of the strata, we were able to make this map. And then from the map we are able to calculate the dip degrees, the dip direction, and from that we get the strike direction. So I hope this sort of problem was helpful. I think it gets you, and I know I wasn't being perfectly exact in the real world and I wasn't using exact tools or anything, but I think it does help you get into the mindset of, okay, we're not just doing textbook problems with these things. These actually are real world problems, right? And I got to tie it into what I've been talking about recently on this channel, which was folds, so special little treat for me. But hopefully that was informative, otherwise good review. Hope you guys enjoyed, and I will see you all in the next video. Ciao!